Hello, welcome to CSC 7132, Operating Systems and Networking. This is Brady Chen. Okay, in section 1.3, we're going to talk about the evolution and the scope of operating system. So we can discuss the operating system based on the evolution of operating system over time, and then we can also discuss this based on the application environment. Okay, so we can actually discuss the operations from these two dimensions. The evolution of computer operating systems are closely related to the development of computer technologies. The first digital computer systems, developed in 1940s, used the technology called vacuum tubes. It's an old technology now, but it was cutting-edge one at the time. The vacuum tubes were used to represent the binary digitals, 0 and 1s. Now, due to the limited size, no operating system support was provided at the time. Okay, and then since then, the operating systems have undergone a major evolution, driven by innovations in technology and the corresponding growth in user needs. Okay, one of the terms is called Moore's law. It is a term used to refer the observation made by a computer scientist called Gordon Moore. It is not actually a law, it's an observation, which says that the number of transistors is another technology after the vacuum tube, in the integrated circuit doubles every 2 years. Now, people use Moore's law to predict the development of technology. Okay, it was pretty accurate. Okay. Now, computer scientists divide computer systems roughly into 5 generations, each basically lasting between 10 to 15 years, and each associated with a major shift in hardware technologies. So each generation is associated with a kind of a new technology. The first generation of computer system use vacuum tubes. Okay, it is a kind of device which is like a light bulb. So when you turn on the vacuum tube, it's just like a light bulb. It's gonna create some kind of light, and there's wires inside with a glass cover, and you're gonna generate a lot of heat when we use the vacuum tube. The first computer system used a couple of thousand vacuum tubes, so it takes the whole office space. Okay. Later, in late 1950, a new technology, it's called semiconductor technology, was introduced. Now, people create an electronic device called transistors. Transistors basically gonna provide the same kind of functionality like a vacuum tube, but the size of transistors is much smaller. Okay. Also, it consumed less power. So this is gonna dramatically decrease the size of the computer system. And then later on, there was a new technology called the integrated circuit, okay, which basically compress a whole bunch of transistors, thousands, millions, or billions of transistors into a small silicon wafer. So create a device that can perform a very powerful operations. Now, as a result, the microprocessor was created. So it basically used the integrated circuits. Okay, and then when more and more actually transistors are integrated into a small component, then people create a new term called large integrated circuit, LIs. And then later, more and more actually transistors to integrate into the small component. It's called a very large integrated circuit, VLIC. Okay. And then with the network, introduction of the network, now the computer system going to perform most of the functionality provided by networking. So they can provide something called distributed computing, and also they can combine the power of the computer systems distributed all over the places to provide a huge powerful machine. Now each major breakthrough led to the development of new generation of computer system, which in turn required major advancements in operating system capabilities. Okay. Now this table basically summarizes the 5 generations of computer systems and also the corresponding operating system types. Now, so the first generation is using the vacuum tube. Virtually there's no operating system. Okay, all the programming was done by experts in machine language. So they even actually, plug the wires into one place and plug the wires in other places to perform the computing. There's no actually operating system. And then using the transistors, the computer size is actually reduced. So then people start to actually store some of the software into a limited actually storage created by the transistors. Okay, so at the time, the operating system used is called a batch operating system. So the operating system is more like an organizer. So when people submit the job, I use the computer to do the computing job, then operating system basically going to organize the job. The input and output. Normally, people use something called punch cards or like a tape, so they can actually import data in there. There were no keyboard or computer monitor, so you can just type the program into the computer system. No such a luxury. So they only use the punch card or the tape. So people basically create the computer language and then convert the language into a very low level, like assembly language or machine code. So then, which is kind of binary digitals, and then they punch this binary punch the hole to represent the various different binary numbers, and then the machine read the tape. Okay, so and then the third generation used integrated circuit. It basically then it allows the development of microchip to replace individual transistors, so they can integrate thousands or a multi-thousand or even like millions of transistors into a small component. Okay, the operating system becomes more powerful. The operating system can do interactive multi-user operating system. So that means the machine can support multiple users. They start to support multi-processing. Okay, so also the time sharing was introduced at the time, so the computer system can actually switch different tasks during the operation. And then when a very large scale integrations, VLSI, is introduced, VLSI allows the placement of a complete microprocessor on a single chip. So a single chip can perform a certain kind of functionality. So this basically leads to the development of microcomputer system, or sometimes it's called a personal computer system. So now the operating system at the time used the desktop and laptop operating system. Now initially they used operating system called DOS, Microsoft DOS, MS-DOS. It's called disk operating system. And then later on in 1990s, they start actually 1980s they start to use the graphics user interface, and then they called Windows operating system. And initially, the graphics user interface was introduced by Apple, the Macintosh, and then Microsoft actually start use the create its own version of graphical user interface called Microsoft Windows. So then this generation, the computer system is no longer used only by the big corporation. The computer system can be used by individuals. And then with the networking hardware, it's the new network hardware enables the harnessing the power of multi-computer systems. So they can actually combine the power of multiple computer systems connected through the network cables, so they can actually create a more powerful computing machine. So these basically 5 generations of computer systems basically represented the different technology at the time. So if you look at the history of computer systems, you will find out that the operating systems are closely related to the technologies at the time. So different types of operating systems are required for different purposes and environments. So if the hardware is more complicated, then the operating systems becomes more and more complicated too. So the requirements on operating system generally coincide with the size and the complexity of the operating system. So the table lists typical operating system types ordered by the size from largest to the smallest. Let's take a look at the table. So based on the size and the power of the computer systems, then the operating system can also be divided into various different types. Now, mostly the big computer system, we sometimes call the mainframe computer system, these computer system requires a very powerful operating system. So the mainframes are large central computers used by large organizations. Okay, for example, like investment company, banks, they're gonna store a huge amount of data, and they need extremely powerful computing capability. So, it's the common application areas are basically high volume data processing in administration, banking, government. Okay. So you require high throughput and the management of large storage. So because you're going to store like 1 million or a multi-million or even 100 millions of customers' information. So these are called the mainframe computer system. And then for most of the computer system called the servers, they actually serve a particular purpose. Okay. Servers are typically a large computer that responds to requests from individual clients. So there are various different servers. Each serves certain purpose. Okay. For some of the server, they store the customer information. They store the software called a database. Some of the server actually performs like a network node. Like a router or something, or some of the server actually performs some kind of house the website. Okay, so each server actually serves a particular purpose. Okay, so the servers, for most of the actually servers, people use this to perform some kind of application like a web and email processings, internet commands, something like this. Okay. So for the servers, mostly people want the server to be very fast response, and also it requires a lot of security. Okay. There's also another kind of computer called multiprocessors. Okay, or sometimes it's called a parallel computing. Parallel computer. Okay. Now, parallel computer is a system which contains a multiple CPUs and memories. They are interconnected by a fast network, so the machine can actually perform a very powerful computing job. And so all these CPU can run concurrently to provide an extremely powerful computing. For example, in the weather broadcasting, so people want to collect the data and try to predict the weather, so they want to actually use the parallel computing. Okay, and then another type of computer is called distributed system. So it's a network of independent computers interconnected via the communication networks. So they can create some kind of a virtual big computer, by combining the power of each individual personal computers. So then combining the power and eventually create an effect like a big computer. Okay, now the computer size becomes smaller and smaller. So let's continue with the table. So, and then the next, the level of computer systems are the desktops and laptops. These are the personal computers. Okay, so desktop and laptop basically perform some kind of operations like word processing, personal finance, like you can run the Microsoft Word document, Excel spreadsheet, and a PowerPoint presentation. Or you can actually perform the computer game and chat with other people. So these are the computer systems that are widely used in, most home. So for desktop and laptop, because they basically target customers with no computer actually skills. So they really emphasize on the user-friendly interface. That's the reason why the Apple iOS operating system, Microsoft Windows operating system. So when people use this type of operating systems, they don't need to have extensive training. So most of the interface should be self-explained. So that's the desktop computer. And then in modern days, people start to use some kind of computer system called handheld devices. They're small, portable, like iPad, your iPhone, your smartphone, and even small like iWatch. So these actually small devices can be pretty small, but don't make it wrong. Some of the machines are very powerful, like an iPhone. They are extremely powerful. So so these handheld devices should be also targeted customers with no computer backgrounds. So they should provide a user-friendly interfaces and easy integration of new applications, support for microphone, speakers, cameras, GPS, motion sensors, and lots of different components that people can use these functionality through the apps. Okay. Now, there's another type of computer systems. It's called a real-time system. You probably don't even notice these type of computer system because so for smartphone you can still see it is a device like your phone, right? So then you can perform a lot of operations. So smartphones are some of smartphones are very powerful, and real-time systems are sometimes embedded in many devices. For example, your TV. Okay, now modern days you can purchase a TV And then some of the TV provider, they call the smart TV, they provide some kind of access, like Fire TV or some kind of apps. So you can actually, there's a small chip building into the computer system, and that small chip is actually a small computer. Okay, so there are lots of things like the computer system in your vehicle, in your car, the computer system in your small air conditioning systems. So these are all the embedded computer system. So sometimes you don't even see the computer system. So these computer systems are not really easy to see. They're not really like a small device in a box you can easily see. So they probably can hide in most of the devices. Okay. And then that's a real-time system. And then there's sensor networks. It's a collection of small, spatially distributed, dedicated sensor communicating by wires and wireless connections. Sometimes these sensor networks, they don't even talk to people. These sensors are connected to your desktop. So every time they just, collect the data, like a temperature sensors that collect the data, and then the temperature, when temperature reaches a certain degree, then they're going to trigger some kind of trigger the software, so the software start to run. Okay, so these are the sensor. Also, these are small chip, Okay, so before we wrap up the first module, the module 1, let's actually recall the computer interrupt. Remember, in the previous section, we talked about the computer interrupt. We did not talk much, but now let's, take a look at an example, and so we can know how these computer interrupt works. Now, in section 1.2, we basically provide a kind of illustrations using the system call to talk about the computer interrupter. Now let's take a look at the example. Okay, so remember, the computer interrupter is an event. Okay, so it's basically a signal sent by the computer hardware to the CPU, and tell the CPU, say, hey, I have some kind of a situation. Please stop whatever you're doing now and process my request, my event request. Okay, so now how does the computer system, perform the interrupt? Okay, so for each, because the interrupter is actually triggered by a hardware signal, right? So that's the reason why when we actually install any computer hardware, install any input-output devices, for each device installed, the computer operating system is going to generate a number, okay, associated with that device. So this number is called IRQ, which basically stands for Interrupt Request Line. Okay. So, for example, if you connect a computer printer to the PC, to your PC. So remember, in the past, you also, when you connect, any device, you need to install a CD, right? We call this a driver, device driver. So the device driver, basically, this is going to actually, once the device driver is installed, you're going to actually allow the actual computer operating system to assign a number for this device. It's called the IRQ number. It's just a number. Okay. So so each IRQ uniquely defines a vector called the interrupt vector. Okay, so let's take a look. So suppose this is the computer memory. Okay, once you load the computer operating system, now in the lower memory side, you're going to load the whole computer operating system. It's a software. And then one of the table you're going to load is called the interrupt vector. Interrupt vector. So it's actually a table. So then this table, one side of the table, one column contains the number 1, 2, 3, 4, 5, 6, 7, 8. So if the table could be pretty long, right? But right now I only put a small 4 items, 1, 2, 3. Now each of the number here, 1, 2, 3, 4, that's the IRQ number. Okay. Okay. So the interrupt vector contains the address of interrupt service routine. Okay. So for each hardware, each I/O device installed on the computer system, when you install the driver, you also install the software piece. That's called interrupt service routine. It's a software piece. So this is executable. Okay. Okay. So now this interrupt service routine is installed somewhere in the computer memory. And then the first instruction of this interrupt service routine is stored in the interrupt vector. And then this is the IRQ for this device. So this is a device, and this is the memory address of interrupt service routine for that particular device. Okay, corresponding to the IRQ that corresponding to that device. So this is actually the second one. This is actually the memory address. Memory address of the interrupt service routine. So you can think about this as a pointer to the software piece. Okay, interrupt service routine. So that's the interrupt vector and the interrupt service routine. Just keep that in mind. Okay. Now, what happens when a computer I/O device sends an interrupt signal to the CPU? Okay, let's take a look at the example. Okay. So take a look at the diagram on the right. Now, this is a diagram for a computer system. Now, this is actually the bus. Sometimes called a system bus. The bus actually connected to various different computer components. Let me actually change the color so I can use the different color. Okay, I use blue color. So that's the bus. The bus basically connect various different devices. Now CPU is connected to the bus, and then memory is also connected to the bus, and then the keyboard, the computer keyboard, is connected to the bus through something called a keyboard controller. Now in modern computer system, the keyboard controller, the controller is actually USB controller. So all the keyboard, mouse are connected to the USB port, right? So it's a USB controller. And then there might be some other devices. for example, like a monitor, okay, computer monitor, and before the computer monitor, there's a monitor controller, and sometimes this is called a graphics card. It's a controller monitor, and that's the monitor, the computer monitor. Okay, it's also connected to the bus. Now, there's also a kind of direct connection, fast connection between CPU and the memory. So they basically bypass the bus. But in order for the CPU to send a command to the monitor, you have to go through the bus. Okay, so bus basically are shared among all these devices. Now, how does the computer system works? Let's actually take a look. Okay, let me switch to the color back to red. Okay, so suppose I want to actually type some text message. So I press the keyboard. So I type A. Okay, type a character A. So the character A will be sent to the something called a buffer area in the controller, the keyboard controller. Okay, so the character A is stored here. Actually, it does not store the character A. It stores some kind of binary digitals, because the computer cannot recognize the alphabet A, B, C, D. So A going to be encoded into some kind of a sequence of digitals. In this case, we use some kind of encoding technique called Ascii. Okay, Ascii code is actually, you basically encode each of the character into 8 digital character, 8 digital actually numbers. So you actually store the binary digital numbers. Okay, so but let's assume that you type A, B, C, D, you just type A, and then the A will be sent to the controller. Now, when the buffer actually receive the character A, now the controller figured out, okay, now someone actually tried to type the characters. So in this case, the device controller basically send a signal to one of the device in the computer system called the interrupt controller, IC. So that's step 2. So this message, the signal, is sent to the interrupt controller, saying, "Hey, please actually, process my request. I'm actually using the keyboard now." So now the interrupt controller gonna basically, the IC, the interrupt controller, basically inform the CPU, send a message to the CPU, say, "Hey, there is an interrupt from a device." Okay. Now let's say the IRQ for the keyboard is, let's say it's 1. Okay, the number 1. That's the IRQ. The interrupter actually, the number which represent the device keyboard. So the IC inform the CPU about the interrupter, say, "Hey, some devices actually request for service." And then the IC also send the device, information such as IRQ. In this case, if the IRQ is 1, it's going to send the 1 to the CPU, say, "Hey, this particular device request for service." Now, when CPU receive the message from the interrupt controller, now the CPU going to say, "Okay, what is the device?" And the CPU check it out. Oh, it's a device with IRQ 1, right? So then what? CPU say, "Hey, I know how to find out that information." So CPU gonna go step 5. CPU gonna go to the memory location, find the interrupt vector. remember the interrupt vector, which contains a table. One side is the IRQ number, right? This column stores IRQ number, and this is the memory address of the interrupter, routine. So the IRQ is 1, so that in the interrupt table, the CPU say, hey, look at the table, and then find the corresponding memory address. Okay, so then this memory address is going to be loaded into the CPU. So CPU start to look at the address. This address basically point to the interrupt service routine for the keyboard. So then it basically start to execute this service routine. So you're going to fetch the first instruction into the CPU memory, CPU actually register, and then start to actually decode the instructions and execute the instruction. Now, this interrupt service routine basically tells what the CPU what to do. Okay. Actually, it will tell the CPU, say, hey, please go to the buffer in the controller and copy the character A from the controller into the memory, somewhere in the memory. Okay, that's basically what it is. So the CPU basically starts to execute the interrupt service routine, which read character in the buffer, okay, of the keyboard controller. Okay, that's basically what it is. So this is how the interrupter works. Once the CPU is done with this operation, copy the data from character A from the buffer of the controller, keyboard controller, to the memory, and then CPU is done its job. And then the CPU gonna go back to whatever it was doing before the interrupt. So just pretending nothing actually happened, but it actually happened, right? So then when people type next character in the keyboard, and then it could trigger another interrupt, and the whole thing just go through again. So this is actually how the interrupter works. So now I think we are almost done with the chapter 1, the module 1. So now we're gonna talk about the interrupter later on in the follow-up chapters. So basically, in the Microsoft Windows operating system, the interrupt vector, remember the interrupt vector, which contains the IRQ number, right? And then the corresponding memory address of the interrupt service routine. Okay, so that interrupt vectors are basically stored in the interrupt descriptor table, IDT. So in Microsoft Windows operating system, the interrupt vector is sometimes called IDT. Okay, so you can actually find out where the table is located using LIDT instruction. It's called a load interrupt descriptor table, something like this. Okay. Now they basically, the user normally cannot change the interrupt vectors. You cannot change the IDT because it's so important. So they don't allow people to change it unless you have actually your super user. Your code is run in the privileged level or level 0. Okay. Thank you.